So far, we've been using the normal distribution to test proportions and difference in proportions. Our focus now, until the end of the quarter, is about testing numerical data. And actually for that, we need a difference distribution. So the normal distribution isn't going to quite work for what we're about to do. Our general approach is more or less the same. We'll determine which point estimate or test statistic is useful. We will identify an appropriate distribution for the point estimate or test statistic, and then apply the hypothesis and confidence interval techniques as we've done before, using the distribution from step 2. All right, well, before I get to the distribution, let's talk a little bit about the conditions. Here, you see on this graph here, there were 136 movies that came out in Hollywood in 2011. Each dot in this graph you see represents the mean from a random sample of 5 movies. So the mean budget of a random sample of 5 movies. So in this case, I take a sample of 5, find the average, do another sample of 5, find the average, do another random sample of 5, and so on. Now, would the normal distribution be appropriate for this? And if you look at it, it looks, if you kind of follow along the outer edge, it definitely looks pretty skewed right. So, no, the distribution is strongly skewed to the right. So, what this tells me is that samples of size 5 are too small for hypothesis testing. Well, what if we took larger samples? So let's try this again. This is going to be the same original data set, except now that random samples were 15. So I randomly sampled 15 movies, found the average, did another random sample of 15 movies, found the average, and so on. And you can see that this graph looks a bit better from the previous graph, but it's still a little bit skewed to the right. So 15, not quite right for hypothesis testing. Well, here's one for 30. So if you compare it to, from 5 to 15 to 30, you can see that this one looks a bit better. I mean, it's not perfect, but it does look more or less unimodal symmetric. So the distribution is unimodal symmetric. Normal model looks appropriate for this. What this tells me is that samples of size 30 are large enough for hypothesis testing. And in general, when it comes to numerical data, we don't talk about successes, failures now, but for numerical data, we'll consider a sample to be large enough if the sample is at least 30. And this motivation for samples to be at least 30, there's 2 reasons. First, large samples ensure that the sampling distribution of samples means is nearly normal. If you saw from the last few examples, the larger the sample, the more closely it follows the normal distribution. And also, larger samples will have smaller standard error than smaller samples do. So then, larger samples would tend to be more accurate. However, as we'll talk about later, occasionally we will look at smaller samples. And with means, we can get away with that if the original distribution is nearly normal. So when it comes to smaller samples, we will use a special case of the central limit theorem to ensure that distribution of sample means will be nearly normal, provided the data come from a nearly normal distribution. That is, if the original data set was normal to begin with, then we can use then the normal distribution is fine for any sample size. And while this seems like a very helpful special case, there is one problem in that small sample sizes tend to be difficult to check normality with small sample sizes. So we should exercise caution when verifying the normality of a small sample. It is important to not only examine the data, but also think about where the data come from.